Hello again. Here is our lesson for areas under a curve. This is for section 25.3 and 25.4 of your textbook. To begin the discussion, I have a question for you. And the question is this. What is the area of the region bounded by the following lines? X equals to 0, x equals to 5, y equals to 0, and y equals to 4. Now, a picture of this, of what I have just asked you, might look like this. So, y equals to 4 is a horizontal line. X equals to 5 is a vertical line. Y equals to 0 is a horizontal line. And x equals to 0 is a vertical line. So the region bounded by these lines is this space right here. So the question is to find the area of this. Now, from very basic geometry, you know that this is a rectangle with length is 5 and the height is 4 units. So that the area is just the length multiplied by the height or the width, which will give you 20 square units. Now suppose instead of that area, which was a rectangle, you have a picture that looks like this one. You have a curve, y equals to x squared plus 1, and you have the line x equals to 4 and x equals to 0. And you want to figure out the area in between, which I've shaded for you here. You can see that that shape is not a regular shape. So it may be a bit trickier to find the area under the curve. Okay, so I want to just show you, just discuss the technique, and then we will go on to deal with some examples. Now, to find the area under this curve, or in this space here, which is irregular, one way might be we can approximate that area. And the way to approximate, let's say that we drew two rectangles under the curve. Now those rectangles will cover some space, but the areas of these rectangles do not nearly do a good job approximating the area under the curve. Now it will give you some area, but it's not nearly enough because you have all this other space that's left uncovered by the rectangles. So these two rectangles that we have here, if we find the area for each one and we add them together, we will get 12 square units. That's an approximation, even though a poor one. A better technique might be to use more rectangles, smaller ones like this. So instead of using two rectangles, let's say we used 8 rectangles, for example. Those 8 rectangles will cover even more area under the curve. But not everything, right? There's still some space in there, right? So if we find the area of each of these rectangles and we add them together, we will get 21.5 square units. Now you can see that's more than 12 square units that we got before, because we have done a better job here, even though we're still leaving some area uncovered. What if we used more rectangles to cover the area under the curve? You will see that instead of using maybe 8 rectangles, if we used 16 rectangles, those will cover even more area under the curve, but there will still be some space in there. So what it turns out that as the number of rectangles you use approach infinity, becomes more and more and more, the better your approximation for the area under the curve will be. Okay, so as the number of rectangles you use approach infinity, as it become more and more, the area bounded by the curve and lines will be reached. So that's what we're going to do here. We're not going to use the rectangles per se. It just leads us to talk about how to figure out the exact area under a curve or bounded by curves or lines. Okay, so in general, if you have a function y equals to f of x, right, and it's the function is one of the boundaries, or and you have x equals to a and x equals to b, so you have this area here. To find the exact area in that space will be to do an integral. So the area is the antiderivative of the function between a and b. That's what I've written here. And that turns out to be capital F of b minus capital F of a, where your f of x is the antiderivative of the little f of x. Okay, so capital F of x is the antiderivative of little f of x. We saw that notation in the first two lessons that we did on antiderivatives. Okay, so this thing I have here is called a definite integral, as opposed to what we did previously in our first two lessons. Those were indefinite integrals because they do not have boundaries like we have here. So let's see an example. The example I have here is what I've been discussing for the last few minutes. So I want to find the area under the curve of y equals to x squared plus 1 between the y-axis and x equals to 4. So it's always useful for problems like this to have a picture in mind. So the picture is what we have here. We've seen this before. So what we're going to do is what we just discussed. We are going to figure out the area. The area will just be capital F of 4 minus capital F of 0. Now, to figure out capital F of 4 and capital F of 0, we need capital F of x, which is the antiderivative of x squared plus 1. We know how to do this now. If we take the antiderivative, we will get x cubed over 3 plus x plus c. So now, if we find f of 4 will be 4 cubed minus divided by 3 plus 4 plus c minus 0 cubed over 3 plus 0 plus c. Now, what happens with the constant of integration when you are dealing with definite integrals that we're getting into now is that they cancel out, because you can see here that when you open up the bracket, c minus c is going to be 0, and so your result here will be 76/3 square units. This is the exact area under the curve. This is not an approximation using rectangles. So I'm going to do the same example, but with the definite integral notation that I talked about a few minutes ago. So that will become area under the curve will be the antiderivative of f of x, which is the function we have, from a to b. So that means we are trying to take the antiderivative, which will be x cubed over 3 plus x, and we are taking that antiderivative from 0 to 4, which means we're going to figure out the value of the antiderivative at 4 minus the value of the antiderivative at 0. You can see that my c, constant of integration, is not there. The reason is because it will always cancel out. Okay, so we may as well exclude it. If we evaluate this integral, our result will be the same as before, 76/3 squared units. Let's see another example. Find the area under the curve y equals x cubed, that is between the lines x equals to 1 and x equals to 2. The picture you have in mind is as shown that I have beside here. It's always good to have a picture in mind if you can. So that's the picture. We want that area in that space there. And for what we've talked about a few minutes ago, that means that we want to take the definite integral of the curve from 1 to 2. So the antiderivative of x cubed is x to the power 4 divided by 4, and the boundaries go from 1 to 2, which means that when you substitute 2 in that antiderivative, you get 2 to the power 4 divided by 4 minus 1 to the power 4 divided by 4, which will give you a result, if you evaluate that, 15/4 squared units. I have one more example. Example 3. Evaluate the integral from 1 to 3 of x to the power -3 minus 1 dx. So that's a definite integral. So we're just evaluating this. So all we have to do is we will just use our antiderivative the way we've talked about. Will be x to the power -2 divided by -2 minus x, and we are taking the boundaries from 1 to 3. That will give us -1/2x squared minus x from 1 to 3. So I wrote it because I don't want to have a negative exponent for the variable, and so if you put the boundaries in, your result will be exactly negative 23 over 9 if you evaluate the integral from that point onwards. Okay, so I hope this you understand this. What I'd like you to do now is to try a couple of examples by yourself, and as we did in the previous videos, you should pause the video now and try these examples, and then when you have finished, you can continue the video to see what I have done. So please pause the video now. Okay, so what did you do? Here's what I did. So for the first one, we want to find the exact area under the curve y equals to 9 minus x squared between x equals to 2 and x equals to 3. The picture you have in mind is the picture of the parabola 9 minus x squared, and the area is between 2 and 3 on the x-axis. That becomes a definite integral, which if you find that integral, it will be 9x minus x cubed over 3 from 2 to 3. And if you evaluate the values in there, your result will be 8/3 squared units. I hope you got that right. And for the second practice question, it says to evaluate the integral from 1 to 2 of 4x minus x to the power negative 3 dx. If you take the integral, like we've done before, that will be 4x squared divided by 2 minus x to the power negative 2 divided by negative 2 from 1 to 2. Which if you simplify, it will be 2x squared plus 1 over 2x squared from 1 to 2. And if you put in the boundaries that we have, it will just give you 2 times 2 to the power 2 plus 1 over 2 times 2 squared minus 2 times 1 squared plus 1 over 2 times 1 squared. Those are the boundaries, which if you simplify, your result will be 45 over 8 squared units. So I hope you understand this, and I hope it's clear to you. I have some suggested practice questions that I've chosen from your textbook. They are shown, so please try your hands on these, and you can always check the answers at the back of the text. They are odd-numbered exercises, and I hope that this is all clear for you. I will be putting up more videos dealing with the remaining of chapter 25.